So we are going to discuss about the alternative clustering. If you still remember, the clustering is unsupervised learning. There is no response. There is no target in the data. Okay. If you check on the syllabus, I want to explain everything, but due to the time, I guess I need to limit the contents. Okay. So this material will be related with the density base and then grid base and how to evaluate the clusters. Okay. So first, let's check the density based clustering method. The clustering methods for the density, it means, density. It is based on the density. Density means, we call this is local cluster criteria. So we are going to find the connected points, the density connected points. The features that we are going to extract is, we can discover clusters of arbitrary shape. Arbitrary. So arbitrary means any shape. Okay. So if you are dealing with the k-means, if you still remember, okay, let's say if I have the like this one. Okay. In the k-means, if you have like non-convex like this one, so k-means is not possible. Okay. With this kind of clustering, k-means is not possible. But that's why there is the method for the density base. And this method can handle noise. And it's only one scan. So it means once you scan all the things, then finish. Okay. So you don't need to do the repetition. In the k-means, you will repeat to find the centroid. So the centroid, which gives the lower error, will be the result. But for the density-based clustering, you need just to do one scan. And you need to have the parameters. Okay, so every algorithms, you need to set the parameters. And this parameter is to terminate the process. Okay. Some interesting study. Today we are going to learn the DB scan. And I think I will not discuss this one. I will not discuss this one. I think I will discuss this one a little bit in the next one. So the basic concept, okay, we need to understand first the concept for the density-based clustering. We call this is DB scan. DB. D means the density. B just density-based. Scan. Scan means we are going to scan. And there are two important parameters, which is EPS and minimum PTS. EPS means the maximum radius of the neighborhood. Do you still remember radius? So if you have like this is the center point. Okay, like we have a lot of data. So we have like this one is the radius. Okay. So any point in the radius, we will check. So in the clusters, we have some terminology. Okay. We have the centroid. We have the center. We have also the radius, and we have the diameter. Okay, so those are the important concept for clustering. And in this case, we are going to use the maximum radius of the neighborhood. And this is the parameter that you need to set. Minimum points. It means the minimum number of points. So points is the number of objects, okay, in an EPS neighborhood of that point. So let's say if I have this one, I have minimum PTS is 5. So there should be at least 5 points. Okay. There should be 5 points in the radius 1 centimeter. Okay. So maybe this one is, yeah, this is the P is the center, and yeah, this the radius equals to 1 centimeter. Okay. So in the radius 1 centimeter, there should be at least 5 points. And if there is 5 points, then we can put it into one cluster. Now we have the N. The N EPS P. It means I want to check from one point, okay, and I want to check for another point, Q. So I have oops, sorry. I have P, which is a point, and I want to check if Q belongs to the density or not. How can we check? So we need to calculate the distance. The distance, you already know, there are how many distance measure? We have the Manhattan, okay, we have the Euclidean, and we have the supremum. Okay, so depending on the distance, yeah, that will be the number here, and the distance should be less than equal to the EPS. So EPS is the radius. There are some concepts. Directly density reachable. Directly density reachable means a point P is directly density reachable from a point with regard to the EPS and the minimum point if P belongs to the NEPSQ. Okay, so NEPSQ is this one. The condition should be the distance is less than EPS. Okay, and then core point. We have the core point. What is core point? The core point is the number. Okay, so this one we have this symbol. It means frequency or the number. Sorry. So this, yeah, this line means the frequency. If the number of EPSQ is greater than minimum PTS, then yeah, that's the core point. So it is the directly density reachable. Okay. I can select this one. P. Okay, this is the P. And then I know that the EPS is 1 centi. So this one is like 1 centimeter. And there should be at least 5 points. So 1, 2, 3, 4, 5. Okay, because I have 5 points in the radius 1 centimeter, then I will make this one as one directly density reachable. And then you can make, for example, you can put another point. For example, this is P. Okay? So you can also again make another radius, and in one radius, like 1 centimeter, how many points are available here? If there are more than 5 points, then it can be also 1. So the concept, there are two more concepts that you need to understand. The first is the directly density reachable. Okay, the first one is directly density reachable. The next is density reachable. The density reachable means I have EPS, I have min PTS, and if I have P here, and I have Q here, there is a chain. Chain. You know what is chain? Chain. Why? What is in Korean? Okay. Anyway, so if there is a Q, and then I have P, then if there is another point P1, P2, P3, P4, and so on until P. Okay, so if I can reach P from Q from any other point, so I can say this is density reachable. You can see here, this is the Q, and then this is P. So I can reach P from any other point. Okay, so for any other point here, I can reach P. Then it is density reachable. Okay, and the other is density connected. In the density connected, a point P is density connected, a point P here is density connected to a point Q here with regard to the EPS and E minimum points. If there is a point O, what is O? Here is O. Okay. There is a point O such that both P and Q are density reachable from O. So here O is reachable, P is reachable from O, and Q is reachable from O. So we call this is density connected. In the density reachable, usually we have only 2 points like Q and P. Density connected, we have the Q and P and the point in between, which is O. Test. Hello. Sorry, something wrong. Can you hear my voice?
Yes, sir.
Yeah.
Yes.
So my device suddenly off. I don't know why. I think it's the internet problem. Okay, let me share the screen again. Oh, okay. Anyway, I think I will upload the videos of today's lecture. Yeah, we have the density reachable and we have the density connected. And as I mentioned to you, the density reachable, we have the 2 point usually. We call it reachable if there are 2 points can be reached each other. Connected, usually we have another point which is O to represent like the middle point. Okay. So the other things that we need to understand is the DB scan. We call this is the density spatial clustering of application with noise. So the spatial means like the we can see from the word, okay, the earth. Usually the earth is also the spatial. Okay. How can we define the spatial? This one is the earth have the longitude and latitude. The idea is also the same with the spatial. We have the X and Y and we want to know the density. It is relying on the density-based notion of clusters. So the cluster will be a maximal set of density connected points. So let's say this is the core. Okay, I have the EPS equal to 1 centimeter and I have the minimum points is 5. Okay, so this is based on the previous parameter. And yeah, I can check every node here. Let's say I have this one. Okay, in this node, I need to have the radius is 1 centimeter, and there should be at least 5. So this one is the cluster. And then if you check this one, okay, let's say if you put the another radius 1 centimeter, okay, so it might be 1, 2, 3, 4, 5. Okay, there are 5. And then if you want to put another like this one with 1 centimeter, maybe this one. Okay, so the density can be many. Okay, so like this one, in one node, there can be another cluster. There can be another cluster. There can be another cluster, and there can be another cluster. So there can be many clusters in one EPS. Okay. As long as it is it satisfies the condition with the radius 1 centimeter and the number of minimum points. So we will create the clusters. We can create another clusters. We can create another clusters. Okay. And we call this is the core. If we can make it as one cluster. We call it border if it is in the line. Okay. So something like this one. This is, we call it like border. Okay. So this we call it border because it is almost on the line. Okay. So this is on the line, not in the center. We call this one is outlier because there is nothing. There is no other object in the radius 1 centimeter, and there is no at least 5 points. So this is the outlier. Okay. That's why it is very good to find the noise. To discover clusters of arbitrary shape in spatial database with noise. So this is the step of the algorithm. We need to select the P arbitrarily, and then you can retrieve all points density reachable from P with regard to EPS and the minimum PTS. If P is a core point, then make it a cluster. If P is a border point, so there will be no points or density reachable from P. So if there is no further density reachable from P, then let's use next point of the database. So continue the process until all the points have been processed. So it means if I take a look on this one, okay, I think I will go to the example. So we have 13 points, this one. Okay. This is the X, this is the Y. And let's suppose I use the EPS. EPS is the radius, 0.6, and the minimum points is 4. So at least there are 4 points in the radius 0.6 and make it as one cluster. Okay. What will you do next? So you need to do the distance calculation. This is the result of the distance from 1, 2. Do you still remember how to calculate the distance using the Euclideans? Okay. Maybe just one, let's say example. Okay. I think for the easy. Okay, let's see. Euclidean calculator. Okay. Euclidean distance. So let's say I have 1, 2, and then I have 3, 4. Okay. So the result will be 2.82 something. Okay. So you can check from the PPT. Oh, where's this one? Okay, the result is 2.8 something, and then the distance from 1 to 3 and 4 is 2.8 something. Okay, so you can measure all the distance. So this number is the distance from 1, 2 to 2.5, 4. This is the distance from 1, 2 to 1, 5, 2.5, and so on. So from this, let's check the EPS 0.6 and whether it fits with the minimum points So we need to check for every point. This is 1.2. So which one is in the radius? Which one is the node that belongs to the radius EPS? Then we need to check this one. Is it less than 0.6? No. This one less than 0.6? No. This one less than 0.6? No. 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 Yes. Okay. So we put this 1.2 and 2.5 into the neighborhood points. Okay. And then check again. 1. No. 3. No. 0.5. Okay. This is okay. So we put 1.1, 2.5. We put this is the neighborhood point. Okay. And then no. No. So from the point 1, 2, there are 2 neighborhood points. Next, you need to calculate the distance. Okay, you need to calculate the distance from 3.4. So you will have like the X and Y and the distance from 3.4. Okay. You will do the same like what I did before based on this table. And you will check according to the EPS. If the EPS is less than 0.6, then you will include it into this neighborhood point. So we got this one and this one, and so on. Okay, so we need to scan for all points. Okay. After we scan all points, so we need to check what is the point that has minimum 4. So here we have only 2. Here we have only 2. We have only 3. We have 2. We have 1. Okay, this is we have 4. Okay. So we can say that this can be one cluster. And this one we have only 2. Then it's not satisfying the condition. And this one, oh, we have 4. Then we can create this as one cluster. Here we have 2. Okay. In this number, oh, we have, oh, sorry. Oh, in this node, we have nothing. In this node, we have 4. Okay, we can make a cluster. But if you check the details, okay, if you check the distance between this point and this point, they share the same information. Okay, because they share the same information, then they are in the same cluster. Or about the other two, nothing, nothing. Okay, so from this result, okay, from this result, from the left one, from this result that I explained from the previous slide, we can say something that this is the border point. Yeah, this is border point, this is border point, this is border point, this is border point, and this is the core point. Because this point contains the EPS and minimum points. So there are minimum points equal to 4. Okay. The next node is border point. This node is core point. Okay. This node is another border point. What about this node? Oh, this node is outlier. Why? Because there is no neighborhood point. The next node is core point because it contains minimum 4 points. The last second is outlier and outlier. So from this result, we can make clusters. The first cluster, cluster 1, is the point 3,4, 2,5.4, 3,5, 2,8, 4.5, okay, and this one. So this is one cluster because we need the minimum point equal to 4 and the EPS equal to 0.6. This is the cluster 2. Yeah, because they have in the radius 0.6 and there are minimum points which is 4. What about the other 3? Because they have no neighborhood. Okay? So the node which has no neighborhood, then they are the outliers. Okay. Okay, can you understand? So I guess, yeah, this is the visualization to show the result. Okay, this is the core point, and this is the border point. The border point means you cannot make another connection with other point because you have only have limited neighborhood points. And this is one example of the outlier. And you can see from the visualization, there is no other point which is in the range of EPS 0.6. So from visualization, it is easy to see. So this is outlier, this is outlier, okay? But the algorithm should do something to check the outliers. So the DBScan can do, and there are clusters. The first cluster here and the second cluster is here. Okay. So the DBScan, it is mentioned that it is sensitive to parameters. Yeah, if you check from the previous example, if you increase the parameters, like the EPS equal to 0.8, yeah, is maybe it's wider. Or if you put the EPS more, like the EPS equals to 5. Okay, so yeah, it contains many nodes. So it's very sensitive with the parameters. So those are the examples. So the A is the minimum points for, and the EPS is 0.5. And the B is EPS equals to 0.4. Okay, so the result is different. You can see this is the color. Okay? This is the color. Yeah, the color is different with this one. So it's very sensitive. You have only a slight small number difference of the EPS, the result will be different. Also, this figure. Okay. In this figure, we have the EPS 5, 3.5, and 3.0. When it is high, like 5, the result is quite good. We have 2. But when the EPS number is decreasing, yeah, the result is not that good. Okay. There is another algorithm. We call it the Clarence. Okay. For this algorithm, I think I will not discuss the detail about the Clarence. Just simply showing the result. If we are using the Clarence, so this is the data. Okay. Based on the data, we want to find the density. So the density means, yeah, like this one. I know this is the one density. This is another density. This is another density. And this is another density. And for this one, I have this density. Okay. And this is another density. This is another density. And this is another density. For this one, we have one. We have this is density. This is another density, and this is another density. If you use the like k-means or other type of clustering, like the hierarchical clusterings and also Clarence, so the result is something like, yeah, you cannot get what you want. But using the DB-scan, you can see, yeah, it is based on the density. This is based on the density. So you can get the result based on the density of the points. Yeah, that's the density-based method. For the next, we can learn about the grid-based method. The grid-based method, it means we have the multi-resolution. Do you know what is the meaning by resolution? If you know camera, okay, your camera have resolution. It means if your camera is good, the resolution will be high. If your camera is not that good, then the resolution might be low. So we have multi-resolution. It means there are many type of resolution. Maybe you have like the, if you have the picture, this is high resolution, and then low resolution. And then let's suppose, because the high resolution is very big on the size, okay, big size usually, and then this is low size. You want to make it a low resolution with low size, but how can you figure out to reduce the resolution and the quality should be good? Usually if we downgrade the resolution, the quality also will be bad. So with the clustering or the grid-based clustering, we can use the multi-resolution grid data structure to do something for this one. There are some interesting methods. I will not discuss the detail, but I will just discuss the concept. Okay, STING. It is statistical information grid approach. So with this statistical information, we can figure out what is the best clusters. We can also use wave cluster. This is the multi-resolution clustering approach using wavelet method. Do you still remember wavelet? Okay, in the, I forgot, chapter 2, chapter 3. Okay, we learn about the simple wavelet method, and we are using that one to we use the wavelet method at the time for the dimensionality reduction. So we can use that method in order to make the clustering. Okay. So if you check on that chapter, there are two purposes of the wavelet. We can use it for the dimensionality reduction, or we can make it for clustering. And there is another method, we call it click. So click is a method for grid-based and subspace. So let's check later. Okay. Sting. So the Sting is a statistical information grid approach. It is based on the spatial area, and it is divided into rectangular cells. So usually we can say something like let's say you have the Korea Peninsula. Okay, because this is the first layer. And if you want to do more clusters from this Korea Peninsula, you will have like Seoul, Incheon, for example, Busan, okay, Jeju. So this will be the I-1 layer. So the first layer is the top one, and the next is the I layer, okay, or we call it the I-1, and the last one is the I layer. So it can be 1, second layer, third layer, fourth layer, 5 layer, 6 layer, okay, and so on. And there are several levels of cells corresponding to different level of resolutions. For example, this one, maybe if we have one cell, okay, if we have one cell, this one, if we go to the next layer, there might be 4 cells. Okay. And then if we have, this is another cell, okay, this is one more cell. And then if you go to the next layer, it can be like maybe 6 cells. Okay. So the different layer may have different cell. And we can say something about this cell, yeah, to make the clusters. So the Sting clustering method, it is based on the cell. So each cell at the high level is partitioned into a number of smaller cells in the next lower cell. So like this one. Okay, maybe I can draw again. If we have one cell, this one, and then I have the lower one, for example, 4 cells. Okay. Statistical info of each cell is calculated and stored beforehand and is used to answer queries. So the statistical info, something related with the, how many data do you have? What is the mean or the average? What is the S? S is the standard deviation. Okay. What is the minimum? What is the maximum? So we call this is the statistical info. Okay. So this is the statistical info. And also we can show the distribution like normal or uniform and etc. And it uses top-down approach to answer spatial data queries. So if we have this for, okay, and then I will do with the small layer again. Okay, start from a pre-selected layer, typically with a small number of cells. So we set like this on 4, and then we set again this cell. For each cell in the current level, compute the confidence interval. You know, confidence interval. Oh, what is the Korean? Yeah, you can check the Korean. So the confidence interval is usually, if we use the normal distribution, okay, if we use the normal distribution like this one, we have like this confidence interval. So if the data is in this range, then I can say that the data is in the distribution normal. But if the data is out of the range, then yeah, it is not normal. So if the data is in the confidence interval, then make the data as one cluster. And after you know that, okay, this is, if you still remember the t-test in the statistical, okay, in the statistics, you have the t-test and we can do the calculation. If the t-test with p-value less than 0.05, okay, if it is significant, then okay, we can say if this normal distribution, yeah, check the lower layer again to find until you cannot get the proper distribution. So until you cannot get the proper distribution, then you will finish and you can say that, okay, the cluster of the first layer is this one, the cluster for the second layer is this one. That's why. So that's based on the statistical information. So this Sting algorithm, it will remove irrelevant cells from further consideration. So usually you will have assumption. Your assumption. Let's say I want to have the normal distribution of my data. Okay, so you just calculate the data. If it is normal, then yeah, you can put into one cluster. And when finished examining the current layer, proceed to the next lower level. Repeat this process until the bottom layer is reached. Okay. So yeah, we just remove the irrelevant cells to make the clusters. The advantages is it is query independent, easy to parallelize, and incremental update. And this is K. It means if you still remember the data structure, okay, K is like linear. The computational of this algorithm is only linear, so it will not give you a high computational. So K is the number of grid cells at the lowest layer. So if you have like 1, and then you will go to the next layer, and then you will go to the next layer from this cell. So it takes only like, yeah, 3 times. These advantages, all the cluster boundaries are either horizontal or vertical, and no diagonal boundary. So this one is just from the top to bottom. Oh, okay. I guess I will stop here. I will continue the click on Monday. Okay. Any questions until this?